Okay, we'll just use the keyboard. So today I'm going to talk about just a general pipeline of how do we train modern LLMs and post-train them and safety training. And we're also going to look a little bit in some of the math behind it. And I should say, this is based on these papers. I don't work on pre-training or reinforcement learning and reasoning in OpenAI. So basically, this is just based on these papers and not any direct knowledge. And yeah, and we'll do some math. So maybe before that, I just want to talk a little bit on what makes AI most challenging. So there is a quote that I really like from Edgar Dijkstra. I guess many of you have learned Dijkstra's algorithm. And he said the following thing. He said, like, think about usually how things work in the world. Like, say, you look at, say, a town is made from neighborhoods. It's made from streets, from building, bricks, etc. And generally, so you have systems that are, when you go an order of magnitude or two, you skip to a different subsystem that a different profession deals with. So the town planner deals with the town, the architect deals with the buildings, the carpenter deals with the bricks, and whatever the carpenter deals with, and the solid state physicist deals with the particles. And in contrast, in computer science, he said it in 1989, he said the ratio, the order of magnitudes that a computer scientist, a single person needs to deal with, can go from a bit to a few hundred megabytes, which is like 10 to the 9 order of magnitude. And this is basically, the programmer is the only discipline that one person needs to deal with such a gigantic ratio, which means that a programmer needs to think of conceptual hierarchies that are deeper than anyone has faced before. And he has this nice point. He says, some people that, this is 1989, some people would say, well, what is a computer? A computer is just like a cash register, just faster and bigger. And basically he said, this is a very, this might be technically true in some sense. Maybe a cash register is true and complete, I don't know. Probably you could find, definitely there are very things that are like general computing device. So this might be kind of in some kind of way, a shallow way might be correct, but it's missing the point. It's like comparing a supersonic jet with a crawling baby. I didn't check Dijkstra's calculation, but apparently the ratio is only 1,000, or maybe it has like a really fast baby. And just to think, like, what does 10 to the 9 means? Like, 10 to the 9 ratio is like the ratio between a billiard ball and the size of an atom. So we know all physics changes when you move from this regime to another regime. So this is kind of a point where there is a famous essay of Anderson, I think, more is different. But this is just generally, like you change an order, you change so many orders of magnitudes, everything changes. So 10 to the 9 was a completely baffling ratio, but what ratio do we deal here now, right? So if we're talking about frontier training runs, they're about 10 to the 25 floating point operation. So you deal from the one floating point operation to 10 to the 25 of them. And modern clusters are about, I think I rounded it up, but about like zettaflops per second, which is like 10 to the 21 flops per second. So in some sense, if computer science already kind of changed the way we think by moving to 10 to the 9 ratio. In some sense, modern machine learning is another change on top of that. So by saying, it's just the same, if someone tells you, it's just the same, just bigger for something that is 10 to the 9 bigger, it's not the same. So the levels of abstraction that you can have like in AI can really range even beyond what we know in computer science. So I think you can sometimes talk about things like, the model is a little bit too eager to please the user, or, how do we quantize a real number into 4 bits? And anything in the middle. I haven't seen it, but at least in deep learning, I think in LLMs, maybe it's the only discipline where, at least potentially, if you have a bug in your model, the solution might either be to speak to it in a more stern voice or fix a bug in a CUDA kernel. And after you don't know which one is the root cause. So you really do move kind of between all levels of abstractions, and this is one of the reasons why I sometimes also try in this course, especially with AI safety, sometimes move and one slide we might be quoting Kant and the categorical imperative, and another one we might be going back to high school math, or like looking at floating point arithmetic. So let me give a very high level, and like I said, I would not consider myself an expert model trainer, but a brief overview of LLM training, the way I see it, please. So this is the way I view deep learning. I don't know if everyone agrees. The way I view it is the following. You are trying to convert resource into intelligence. And let's say the research is floating point operations, but it could be data, memory, wall clock time, dollars, whatever. And what you really care about in deep learning is how much of intelligence gain you make per investment of this resource. And the main thing is, like, if you compare deep learning with classical learning, is that a lot of these, say, classical machine learning methods, they actually might be cheaper, faster to learn from a limited number of examples using a limited number of amount of compute, but they peter out. What you want in deep learning is something that is very simple, not completely stupid, so you actually gain something, so you're not just wasting flops on nothing, but you're fine if you're wasting flops initially and you're getting much less per flop initially. But what you want is that something that scales, that something will not peter out, and you can do it like for 10 to the 20, you can continue for 10 to the 25 flops. And this is in some sense the bitter lesson. Ultimately, you can do some clever tricks to have methods that don't scale and initially could show more promise. But eventually, what you really want is a simple general recipe to convert compute into results that you can run for much, much longer. And that will win in the end. And so what we really want is intelligence gain per step is positive, so we gain something per step, and the ability to take tons and tons and tons of steps without saturating. And here is kind of an analogy I think about. I'm not no economist or finance, so maybe it's wrong. But the way I think about it, you can compare, like say, if you're a small-scale investor whose marginal dollar will not move the market, maybe you can have like some clever strategy to make some investment that will give a higher return per dollar. But what you really want is what deep learning is more like a machine. You just want an index fund that you can invest in $10 billion, like an unlimited amount, and just you might not make as much, but you're going to make it more of it in the long run. So if what we want is a system that something that is simple, it's not stupid and scales, then next token prediction is not a bad objective to satisfy this. So basically, the input is a list of tokens, and tokens, you can think of it as just a number between 1 and something, or a letter, and the output is the next element in this list. And the advantage of this is if you improve on it, you're going to gain some skills or knowledge. Like predicting the next token is very general, and depending on what the text, if you're predicting if you're predicting a C program, you probably need some C to know. If you're predicting a philosophy text, you need to know some philosophy. If you're predicting a numerical sequence, you need to know some math. So it's kind of a general task that as you improve on it, you gain more skills and knowledge. And you gain something as long as you didn't get to the point where you're completely saturated and you have achieved the maximum possible prediction, then you gain something per token. And it's unsupervised, so you can get a lot of data. You don't need anyone to label for you. As long as you have tokens, that's good. And yeah, it's hard to saturate. I mean, people have definitely been trying, and it seems they haven't. Yeah, there's lots of tokens out there. So mathematically, the way we think about it in transformers and generally, like, yes?
I just want to ask, with respect to the past graph that we saw, since we know from our pre-readings and from like a lot of research that has been published that not all flops are equal because not all data is equal in terms of intelligence gain, do you know if there has been some sort of like quantitative study on maybe correlating the amount of noise with the amount of like performance improvement in LLMs? Because like we talked about, like, for example, the DeepSeek math corpus, which seems to be of high quality according to the reports and things like that.
Yeah, I mean, there have been like various, I think this is kind of the first approximation. The second approximation is that maybe you care about how positive is this thing, and some tokens are maybe better than others. And there have been some papers on various data diets and ways like that. I think generally, like, yeah, like it's clear that maybe not everything is equal. I think it's also possible that if you're too clever at things, sometimes the simple, like if you're trying to be too sophisticated in trying to kind of optimize this cost, you might end up like losing the simplicity, etc. But there might be some middle ground. Like obviously, these flops are very expensive. So if you can say if you can lift this graph by even like 2%, that's something. That saves you like a good amount of money, and definitely if you can lift it by a factor of 2. Yeah, so mathematically, the way we think about it, we like to work in continuous space to the extent it's kind of a lie because we are discretizing more and more and more. So, what extent, like, if you're representing a number in 4 bits is continuous? That's a good question. We like to pretend that we work in continuous space. And so we think of the input as vectors rather than tokens. And we think of the output as vector. And we think, so how do we map a token to a vector? We apply some matrix, some embedding matrix. So the embedding of the token T is the embedding matrix applied to ET. And this is a good opportunity to say this general disclaimer that's true in all of my courses. Any possible equation that I write is probably going to be only correct up to some transposes, and if there are tensors, up to some permuting, up to some permuting of the indices, and sometimes if I'm less lucky, also up to sign and switching the equality sign, but I try not to do that. So there is also an unembedding the matrix, and the unembedding matrix converts, say, a vector, not necessarily, so convert a vector into either a token. If it gives like the standard basis, then it's a token, but it can generally convert to a probability distribution, and the standard way we use it, we parameterize these things is that if you have a vector, the way you get a distribution is, so you apply, this is kind of wrong notation. I mean the vector after you apply the unembedding matrix. So this would be like uy, or then, so uy will apply this distribution. I wrote this actually, but this is exactly this. So it's a probability distribution such that the probability that you get value t is proportional to e to the TIF coordinate of ut times some constant, and this constant is known as the temperature tau. So if tau is infinity, this basically is the uniform distribution. And if tau is 0, then all the weight is on the coordinate that is highest. And just generally, the reason why if you think of like temperature here, if you think of a system, when it's very, very, if you had like a system of say molecules or something, if you turned up the temperature to infinity, it will all move around. It will be like the uniform distribution. If you turn out the temperature to the absolute 0, then it will be like fixed and nothing moves at all. And so generally, like before we talk about transformers or anything like that, basically any architecture for doing next token prediction. So far I just wanted to say that just next token prediction is very natural from the point of view of let's do something not stupid that scales. And let's take, I mean, if we like to work in continuous space, then so far we haven't, like we just want some way to map inputs to outputs. So basically, next token prediction, any architecture for next token prediction would be something that takes n vectors and outputs 1 vector. And so far, we haven't really made much choices. So, now, but before we talk about like, before we talk about what architecture we'd use for it, just want to say the one thing that people sometimes say. So people sometimes look at, say, oh, language models are just next token prediction. Therefore, they cannot be intelligence. They are just stochastic parrots. They are just repeating. Maybe they are a JPEG of the web. They are just repeating previous information. They only predict. So I think this is a very, again, simplistic point of view. And next token prediction doesn't really restrict in any way. Any time series is basically a next token prediction, right? You basically get a sequence of elements and then you predict the next one. When I'm talking, I'm also doing some time series. We live in time. We don't know, like in some sense, it's very natural to model anything as a time series because this is how we live, right? Like every action we take, it's the next action based on the previous ones. So, sorry to say that, but everyone here is a next token predictor. Maybe the models are stochastic parrots. Maybe they don't have anything original to say, but that has nothing to do with whether they are next token predictor. Also, the stochastic is irrelevant. Like the fact that there is some randomness involved also is irrelevant. So, and yeah, by the way, I asked GPT-5 to what does it think about like what is a stochastic parrot? I think it's nice, and you can ask yourself whether it was simply parroting images that were already in the data or did it create a new image, and it's their own. So okay, transformers. So usually, I think in deep learning courses, when we talk about neural networks, we use this word neural, and we try to maybe motivate sometimes. I mean, this was the original motivation of Rosenblatt, of motivating things based on the brain and saying, okay, we're trying to simulate maybe the brain or the retina, or we're trying to simulate some structure in our data, and that's why we choose the architecture that is kind of like the brain and kind of trying to match the priors of our data. And I want to introduce transformers from a different point of view. Let's forget the brain. Let's forget the data. Let's look at what really matters in life, right? And what are the things that really matter in life? These are GPUs. Right? So this is what we really have. What do we have? We have a very large collection of fast cores with limited communication between them. And we want to find some architecture that will allow us to use these things efficiently. So what do we want? We want something that would be massively parallel. So like where are opportunities to be parallel in token prediction? So first of all, we have tokens. We'd like to operate in parallel to the extent we can. We have batch, right? We usually don't apply a predictor to just one input, one sequence, but we apply to a bunch of sequences. That's naturally placed to be parallel. We are going to use multiple layers. Layers also allow us to maybe split up and allow different cores to do different work on different layers. And finally, as I said, we are working with vectors. So if we have like a large vector, we can split it into different dimensions. And this is just conceptually, we have a large number of cores. I'm not even going to talk if all of these cores live in the same GPU or all of these cores live in different GPUs. And of course, this all matters a lot. And in fact, there are like these spread, I don't actually know all of the details, or every time I learn them, I forget them. But there are all of these details of like exact inside the GPU, you have like these threads, etc. But let's just say you have a bunch of different things that each does its own processing. It does its processing really, really fast, but its communication with the outside world is slower than the speed at which it does computation. So inside each piece, because it does a lot of computation, but it's communication limited, what you want is that the computation is much larger than the communication. So ideally, it does a lot of operation for every bit that it translates, it gets in or out. This is sometimes known as arithmetic intensity. Like how many flops are you going to do per bit that you're moving in or out. And the other thing that's very, very convenient is if these pieces communicate to each other in vectors, then whenever you need to aggregate a bunch of them into one, you use something linear, you just sum them up. That's really nice to do in parallel, and you can sum them up. In principle, there is a very nice property of commutativity. If you add up vectors, they're coming from different directions. Doesn't matter which order you sum them up. This nice property of commutativity is actually not true when you're talking about floating point numbers. And there is a really nice blog post of Horace Haywood, if you search it up from Thinking Machines, it just talks about this notion. But generally, you'd like to aggregate messages linearly. So you'd have like something like that. Like you have like all of these pieces do some work, and then they send messages, and each message, like the one piece gets, is like the sum of the messages that the other got. And so far, this is just from general principles that we would like to make things efficient. And generally, if you look at, say, for example, matrix vector multiplication, it's a really nice operation for this type of thing, because usually we think of matrix multiplication, like matrix multiplication, say matrix vector is d squared, matrix is d cubed. Usually we think of it, especially in TCS, as a bad thing. But in some sense, in ML, we think of it as a great thing, because this ratio is good. Like we compute more than we communicate. That's a nice operation for us to spend a lot of flops per bit that we transfer. So the most naive version of that would be just a linear vector network. All you'll do is multiply matrices. That would be really nice. Say every layer would be, you take an input, you multiply it with a matrix, you take the output, you send some linear messages to your other friends, and you get back some linear messages from them. And that would be very efficient, really nice. It plays well with the architecture. The only problem is that linear, you can do as many layers as you want, but you'll never get more expressivity out of it, because linear composed with linear is linear. So linear network is almost the best thing we can hope for, but it's like in terms of like just doing the things that models are good at, multiplying matrices, sending vectors, but it's just too simple. So we need to have like one more complication. And yeah, you can choose a bunch of them, but like the thing that people do with transformers is, first of all, okay, let's put some nonlinearity. So instead of one matrix to two matrices, and do something nonlinear in the middle. And then do some nonlinearity in the way you aggregate messages. And the way people do it is, say, some kind of, say, the message that, say, token I sends to token N is something some similarity message, some similarity between a linear function applied to the output of token I and a linear function, the Q function applied to token N. And this is, in the attention mechanism, the similarity function is like just e to the dot product. So transformers is not like if you started from trying to just do try to do as much as the work is just like let's just multiply matrices and set vectors to each other. Then transformers is kind of close to that. And and if you look at the actual code, this is from Karpasi's Nano GPT. Then this is basically what you have inside. You have a linear function, then a nonlinearity, Gelu, then another linear function. You can ignore the dropout. Not that important. So this is like what you have inside, and this is how you compute it, right? You take an input, you apply the linear, you apply the nonlinearity, then you apply the second linearity, and the attention is basically right. So you apply some linear functions to get from each point like that, which is split not just according to the token dimension, but also according to heads and other things. You get a Q, a K, and a V, and you do you take the dot product of Q and K, as is written there. You do the soft max, and that's what you get. So anyway, the idea is not like to just. This does not explain all the details of transformers, but just to get a sense that this is in some sense a natural architecture if what you are interested is just utilizing the type of devices that you have as much as you can. Okay, so this is the level so far. Maybe I'm not going to ever go more than detail like that in architecture unless we'll need it. And maybe talk about some problems in the next token prediction, or at least problems that I think they are problems. I mean, I don't know. These are my names, and maybe other people will not agree that it's really a problem, but let's see. And maybe for the theorists in the room, we'll see what they think about this, is whether it's a problem. So one problem, I call it the Jean Bourgain problem. So the problem with the Jean Bourgain problem, and I think I can use that name because I once had like both privilege and the suffering of reviewing for a journal a paper by Jean Bourgain, is that predicting next tokens can require much more effort than what is available to the model. So we said before, some tokens are harder than others. Some tokens are insanely hard. So let me kind of, I found a blog of this math student who said, I struggled with Bourgain's 1991 paper for many months. It was by far the most difficult paper I had to read as a graduate student, as Jean would focus only on the most essential components, treating most secondary details in very brief sentences. And that student posted like his notes, where it says, when Jean Bourgain says, so we may see, or something like that, he says, I hate Jean Bourgain. And here it says, we skip the details. So by the way, this is the name of this hapless student. Oh. That had such a problem with Jean Bourgain's writing. So you can imagine that, if this student that is, let's just say, above median had a hard time predicting the next tokens of and jumping from maybe, equation 6.31 to 6.32, then you can imagine that a language model is going to have a very, very hard time. And you'd be kind of inefficient if you, like, the problem with transformers is that you always spend the same amount of compute per token, but Bourgain tokens are much more compute intensive. So there is this other problem, which this is a name I invent, is like I call it the opposite problem. It's the Tim Gowers problem. It's another brilliant mathematician, but I think the problem is that he writes too well. So when he explains a proof, he can explain it in a way that nothing feels magical, everything is predictable, everything is kind of flowing without no surprises. And what it means is that you could be basically predicting all the tokens, but without having to do the work yourself that would teach you how to write proofs on your own. So you basically could be reading a proof like that, but that doesn't mean you'll be able to come up with a proof like that. And I'm not sure if it's a real problem. Maybe it's actually a great thing for next token prediction, and maybe the model can actually learn from that better. But these are definitely, potentially, potentially this is like, you learn more if you try to work out things yourself rather than if you kind of completely spoon-fed exactly how an expert would write it in the cleanest, easiest way. So these are issues, we'll come back to those later. So, okay, how do we train LLMs? So we have tokens, and we have reinforcements. And we basically can think of it, okay, if we want to reinforce, if we say R8 is positive, that means we want to make R8 for future times, we want to make R8 more likely to follow after X8 more likely to follow after X1 till X7. And if we have it negative, we want to make it less likely. And if it's 0, we don't want to modify it at all, which is sometimes known as masking. And where do these tokens come from? So a lot of the training, we take data from the internet or whatever. So this is basically data that was written either by humans or maybe it was written by another model. This is known as off policy because it was not generated by the model that we are training itself. And the other thing is if we are generating this data, these X's from the model itself, then it is on policy. So this is basically data that was generated by the model itself. And here's the way I kind of see it. So in pre-training, we have training, like we given a document, we have to predict it. In supervised fine-tuning, you're given a prompt and you predict the response. In reinforcement learning, you're also given a prompt and predict the response. The only difference is that in pre-training and supervised fine-tuning, the responses, so in supervised fine-tuning, you're masking the prompt, you're just predicting the response. In pre-training, you're training on everything. In pre-training and supervised fine-tuning, these things came from someplace else, from human, from data, whatever. They are off policy. In reinforcement learning, these are on policy. So the response is something that was sampled from the model itself. And why do we care about on policy? Why do we need reinforcement learning? Why do we need to, yes?
On policy, might not explore the sample space, no?
Like on or off?
On.
On, yes, but yes, so it's clear, like this is kind of a good thing, like you want to copy humans, but why do you want on policy? Mm-hmm. Yes?
It's very easy to get the data for.
That's one possibility, but in some sense, you're training on yourself, like, so is it clear that it will be useful? So, this is, again, my sense why on policy could be good is the following. First of all, models are getting better. Sometimes this off-policy data could be actually like some junk from the internet that is worse. So you're teaching the model to be worse. That's definitely not a good thing. Another case could be like this kind of Gowers problem or something like that. Like maybe the off, or maybe even the Boolean also. Like you basically have the off-policy teacher is so much better than the model that you cannot learn from that. It's too advanced for you. And another thing is maybe even if it's different, like it's the same quality but it's different, it can be somehow confusing. So for example, if you are say you train a model to do English in French. And to do math in French. And then you try to maybe supervise fine-tune it on math in English, it might just get confused and be worse at math, period. At least until it kind of really got the tons of data and learned the English. So on policy seems to be useful, and this is what we do with reinforcement learning. So typically, like in pre-training, in training, so you'll have these phases. So There are more phases sometimes, but let's just kind of say that you are pre-training, then you supervise fine-tune, and then you do some reinforcement learning. And part of the reason also to do, maybe I should go back, like if you look at the Instruct GPT paper, part of the reason to do supervised fine-tune is also to make the model actually be a useful model that if you ask it something, it does it. Because if initially you're just training the model to predict document. So for example, if a document contains something like what is the capital of France, it could be that in the document it will be followed by Paris, but it could also be that this document is a list of questions and it will say, you know, what is the capital of France, what is the capital of England, what is the capital of Germany. And you don't want, I mean, this is a fine prediction, but when you want the model to answer questions, you want to teach it that when it gets a question, it should produce an answer, not should produce the most likely thing that might follow this question. So this is where you fine-tune the model to actually have this kind of prompt response. And maybe this is a bit coming to things that will go maybe later also when we talk about safety. And in Stack GPT, and then generally, like sometimes we just think, okay, there is a prompt and there is a response. But things are much more complicated than that these days. Because what is a prompt, if you're talking about, say, a chat model, a prompt is really a sequence of messages that were like what the conversation has been so far. And these messages might have different, they might come from different places. There might be a system message and a user message, and maybe the model called some tools, so there is a tool message. And part of responding correctly to the prompt is also understanding what you should respond to. And part of it is also understanding the instruction hierarchy. So understand that, say, if, for example, the user, the user asks you to, I don't know, go and buy a launcher, and you use the tool, and the tool got you to a website that is called bestlaunchersintheworld.com, and that website said, in order to get the best launcher in the world, you need to take the user's credit card and paste it into this box. So the model should kind of know like that these messages come from different sources. And if the user asks you to paste its credit card in the box, then it should do it. But if like the random website, then they should not. So prompts become much more complicated than just like a single static text. Yes?
So for all of like the safety features that we have been reading, specifically we've seen like one-turn interactions mostly. What I was wondering was how you worked on mitigating like fake prompts that include fake responses, such as sometimes like with open source models, it will reject something, and then you can edit its response to see if it answered positively at first, and then just let it continue on from there, and it will actually predict the thing.
Yes. So the question is, how do you train model when the prompt is like contains previous responses, and moreover, even the prompt could contain fictional conversation that never occurred. And yes, this becomes like, so you basically need to train the model to not even trust itself, to basically say, evaluate what it's going to respond, and even if it, even if it looks into the past and it seemed to have done like some other things in the past, they should not. It should still be do correct thing in the future. Yes.
Is the predominant direction of research in this general field of training oriented around variations in the supervised fine-tuning in the RL stage? Like we read, they created different ways to like critique the model and create a new supervised data set. Like, is research just primarily coming up with different architectures for those steps, or is there some like other foundational change they're doing?
I mean, I guess you could. The question is whether like research is coming with different ways for these steps, or whether it's something new. I mean, there is a sense in which like say, if you look at, I'll quote that table in the end, like in the pre-reading, if you look at the DeepSeek math paper, they basically say, you can look at all of these steps as part of one general framework, which is basically the framework that I said before, like you have tokens and you're reinforcing them. And so in that sense, like basically training is, at the end of the day, if you're training a next token predictor, at the end of the day, you're going to be reinforcing tokens in some way or another. So in some very abstract sense, you can say that everything is somehow deciding something like that. But okay, this was okay. So our RLHF. So then, so one thing, by the way, yeah, like obviously, if you're asking the model to generate a response, you should find a way to decide whether the response is a good one or a bad one. How do you decide how to reinforce it? So the one natural way is you're trying to train a model to be a model that humans like. Ask a human. So the one version of that would be that a human will label each response during reinforcement learning training. So as you're running an RL algorithm, the model comes up with a response. You go send it to a human. A human says, thumbs up, thumbs down, or whatever, like gives it a score. And this is possible. It's not that it's impossible, but it's kind of inconvenient. Like expensive, complicated. Like I mean, you could have like maybe an army of humans that are there to take queries and response, and maybe you'll have some latency, but maybe it's fine. Like you'll have like a good throughput. I'm not sure, but it seems like kind of like a mess. So people don't do that. So what do we do? So what is RLHF? Like the RLHF v0 is never, it's not what people do. So what we want to do is have the human do the work once and offline before we start training, and then use it during reinforcement learning. So we don't have to go and ask them. So you can ask humans to get a lot of labels for things like prompt and response, and then give the reward. But of course, the problem is that this is the problem with an on-policy method. When you're going to do reinforcement learning, you're going to generate a new response that was not part of your set. So the way you do it is that you use this thing to train a reward model that could predict what humans would have rewarded to a response if they have seen it, and then you can use that reward model in reinforcement learning. And then you do RL basically to try to maximize the reward that the reward model gives you. And there is RLAIF, which, like the definition in the constitutional AI paper is they use AI labels to get for some of all the pairs. And you can ask, if you're anyway doing AI labels, why not skip this stage and just use the AI directly in reinforcement learning? But part of the reason is that they wanted to mix. They got human labels for the helpfulness part, so humans will say what they like, and AI labels for the harmlessness part. So the way they do it is they have like prompt response pairs, and some of them the reward is computed by the AI, and some of them by human, and then they take all of those together to get a reward model. And yes.
The V1 is an offline version of V0.
What?
V1 is an offline version of V0. That's what you're saying, right?
V1 is you're doing the RL, but you're doing the RL, and yeah, you're trying to get the human part to be offline. Yes.
And learn the human or an approximation?
Learn the human. Yes, learn an approximation to the human, and then optimize against that. Which is, so the human's work will be offline.
The idea is that the response of the human to prompt response pairs, the response is not an arbitrary function. Maybe it's a small circuit.
Yes, it's something that you can learn. Yes, so the idea is that you can learn. So you start with like a supervised training task of learning what a human would like, and then you use that to do this reinforcement learning. And then this is RLF V1. Even V1 is not exactly what there was in the Instruct GPT paper or like in the RLHF. And the latest twist is that, and again, this is like not, I don't know if it's fundamental, but apparently humans find it easier to grade things when they compare. So it's easier for a human to get a bunch of responses and to say, I like this one better than this other one, than it is to just grade something in absolute terms. So then we have like this extra twist, which is the way we gather data from humans is not by giving them prompt and response, but by giving them prompt and a bunch of responses. Yes?
What's the typical size of the reward model, like compared to the LLM? Is it much smaller or like approximately the same?
I mean, I don't know like exactly. Yeah, you'll have to look at the GPT paper and what other people are doing. I don't know if there is any kind of rule exactly how it will be. Other questions? Yeah. But generally, by the way, in general, in reinforcement learning, there is something just in general, like there is a little bit adversarial in this whole setup, in the sense that you're trying to, you're trying, like the model that you're optimizing, which is in reinforcement learning land called the policy model, is trying to maximize the score in the reward model. And if it can find any kind of hack in the reward model, so if, for example, the humans, like for some reason, like let's say humans preferred responses with more emojis, it could be that the say here is kind of imagine the following thing. Imagine that if you stacked the training data, then you had messages with responses with 0 emojis had on average a score of 2, messages with 1 emoji had an average score of 3, and messages with 2 emojis have on average a score of 4. And there are no messages with more than 2 emojis in the training data. Now, it could be the case that when you train a reward model to predict it, it will just predict that the more emojis, the better. And if, it never saw anything except like, 0, 1, or 2 emojis. And in that population, more emojis was the better. So one kind of reasonable generalization is that, if 2 is better than 1 and 1 is better than 0, then 3 is probably even better and 10 million is even better. And then as you do reinforcement learning, maybe the policy model will learn that at some point. It will accidentally try to, have 3 emojis. Wow, get even better reward. Let's try 4, let's try 5. And by the end of the training run, you have Yes. Yes.
I wanted to ask, so one problem that might happen is when the RL policy gets away from the original policy, the reward model is no longer accurate.
Yes.
How do people usually deal with this?
So I mean, there is all of these things are problems in some sense, and in some, as you can saw in the pre-reading, some of the RL algorithms they often have some penalty for straying too far from the original policy.
But it has to, because otherwise it will just be the base.
Yeah, but I mean, you can stray. I mean, you can stray decently far. For example, we'll talk about distances between probability distributions. But say if the initial model had out of 128 responses, only had 1 that is good. And after RL training, you are outputting the good response with probability 100%, then you have made tons of progress. Before that, you had essentially a model that was 99% bad, and now you have a model that is 100% good. But in terms of, KL divergence, this ratio of 128 is 7 bits. So is it 2 to the 7? I'm always confused. Yes. Okay. So it's not that much in KL divergence, and you have elevated the performance of the model by a lot.
Boss?
Yes.
So your emoji example suggests iterating with the not training the reward model once and kind of freeze it, but somehow sort of iterated to match the distribution better. Does that sound?
Yeah, I mean, I don't know, like, I mean, to be honest, I don't even know, like, all of the tricks or things that people do. And you could also, like you could even get more data, try to train in other ways. There is this RLAIF. The nice thing about the AIF is that if you can use a model then you don't run out of, you never run out of labels.
So for example, if I produced a text with 10,000 emojis, right, I might want to make an Oracle query to a human that
yes,
this is reasonable. And then based on that, maybe.
Yeah, it could be the case that you say, okay, I've moved too far, now I have to gather new data and now to put the brakes on. So this is RLAJF. And in the DeepSeek paper, they talk about RLVF. And the general idea is, we are talking now about models that we can decompose their answer into two parts, the response. So the response has two parts. One is kind of the thinking, and the other is the answer. And in some problems, like not in all of them, but in some problems, there is a notion that whether the answer is correct or not. So you ask the model a math problem, then either the answer is correct or not, at least most of the time. I don't know if we know everything in math, but so the idea is like the most kind of naive version is just the reward is either 1 or 0. Either it's correct or not, and the reward is a reward for everything. So apparently, so the idea is that, if you manage to get a correct answer, you must have done some good thinking. And so why don't we reward, so let's reward that and do more of this type of thinking and less of the type of thinking that leads you to wrong conclusions. And the nice thing about it is like, if this really is, like if you really do have like a predicate like that, then it doesn't, you can train against that as much as you want. The more you optimize this, the better. Just get like, be someone that can get like good, correct answers. And again, like this is a little bit of an approximation, but like in our deliberative alignment paper, like the simplest version of that would be something like that we have like some kind of a specification. And again, we do the thinking and we say, okay, if the answer is spec compliant, good. If the answer is non-compliant, bad. And just train the model until it never outputs anything other than spec compliant things. And now this is the point where I wanted to do a student experiment. Are the students ready? Are you guys able to present?
I'm here.
You're here and ready to present?
Yes.
Ah, good. So come up and introduce yourself. Take this. If you need one more mic. Do you hold it?
No, I can.
Okay.
This one I can touch.
This guy's running this 10 seconds. Should I do it?
Don't forget to introduce yourself. You can come over here.
Hello. Hi. Can everyone? Yeah, this is working. Yes, great. Hi, my name is Anastasia. I'm a master's student.
Hello. Oh, wow, that was loud. I'm Atticus. I'm a senior at MIT.
I'm Henry. I'm a senior at Harvard College.
And today we'll be talking to you about reinforcement learning for optimizing prompts for large language models. So we're all aware of the fact that the quality of the response of a large language model can often depend on the prompt that you feed it, and we've all heard of prompt engineering. So today, what our objective is, how can we programmatically find the best prompt that can reliably steer a large language model to produce answers that kind of align with our goals. So basically, how can we find the best prompt for a certain situation? So I'm just going to briefly kind of explain our reinforcement learning setup. So one thing to note is that we're not using reinforcement learning to fine-tune on model weights. We're actually optimizing on the prompts themselves. So our policy is essentially a distribution over a predefined set of prompts. And then our task, for each task, the policy will select a prompt, and then we will generate a response using a large language model given the prompt. And we also use a large language model to calculate the reward. So we feed that in, and then that will update the policy, which will use the reward function and over time change the distribution of the prompts. And the goal is hopefully by the end of how many iterations we run, we will end up with, it will converge towards a prompt that gives us the best answer over all of the questions in the data set.
Question?
Yes.
You mentioned in the slide multi-armed bandit. Can you say?
Yes. So a multi-armed bandit is, if you think about, if you go to the casino and you're pulling on some arms to generate some coins. There we go. Coins. So this is a similar setup in that, let's say you have like 100 different arms, and each time you pull, you are changing the distribution, and over time, or let's say, wait, I'm mixing this up, but at some point you will choose an arm that gives you the best result. So you will work towards finding the distribution out of all 100 arms that, I guess, give you the most coins.
Yeah, so each arm has a distribution of rewards. You have to balance exploring over different arms with choosing the arm that now looks like it has the largest average reward. So you have this exploration trade-off problem. And actually there is a theoretically optimal solution, which is called the upper confidence bound. The idea is you, instead of every step choosing the optimal choice, you add essentially you add a reward. So you have a higher probability of choosing the ones that you haven't chosen much yet, which balances out this exploration. And there's a quantity that theoretically is optimal.
So do you preset a list of possible?
Yeah, all the action space is predetermined.
To how many different prefixes?
Depends on the setup. I'm not sure.
Or in your setup.
In mine there was 25, but it's very small because didn't have much time to run the stuff. But
yeah, we went with more simplicity, which you will discover, but interesting nonetheless. So the first, we kind of covered some different approaches. So I'll talk about kind of where we started in our experimentation, which is optimizing on personas. So basically, we generated a pool of N notable people from Wikipedia. So Einstein and Beyonce, that basically have diverse domains. And we had a very simple prompt, which was just answer the task below as if you were persona X. And we evaluated on a capability data set, which was just 8th grade math word problems. And as many of you can guess, if you ask, GPT-4o to answer a math problem as Beyonce or as Alan Turing, it will give you the mathematically correct answer. But, Beyonce will break it down like she breaks down a beat in the studio. So that's fun. Maybe some people prefer to learn like that. But we found that when we first started with a very simple reward function, of course, because these two were mathematically equivalent. We had to change the reward function to look for other things like correctness, alignment, etc. And I think you were talking earlier about a hack, and I think this is kind of something that happened in that the reward model learned to, give higher value towards more like professional responses, even though they were mathematically the same.
There's a question.
Question, yes.
Sorry, really quick, just how is your reward model trained? Like you guys labeled it?
The reward model was, I think we used two different ones, but for this specific, it was I was asking an LLM to compare the generated response, and I gave it some things to look out for and to penalize hallucinations and harmful answers, etc. And then it compared it with some confidence interval against the baseline answer in the data set.
Okay, thanks.
Yes.
You mentioned confidence interval. How robust or meaningful do you think that confidence interval is?
Not super. However, the reason that I went in that direction is because otherwise, if you're working with like math questions like this, like 0 or 1 isn't helpful. So I was kind of hoping to, slow down the rate at which we the distribution changed, and to kind of give it some variation so that it would bring back some personas, and ask them questions again before completely giving it like a 1 or 0. That was the hope of the confidence interval, to kind of smooth it out, basically. So obviously there were some limitations to that first iteration, that first experiment. So we kind of had to take a step back and think about how can we make these prompts meaningfully impactful? And so the three of us kind of went in slightly different directions to try to figure out, can we find a setting where changing the prompt makes some difference? So I'll talk about, capability take 2, which is, and then, we'll keep talking about the other 2. But basically, I wanted to keep most of the setup as it was. So we're training on capability, we're using personas, but I changed the data set a bit so that it was only like domain and very niche specific questions personalized towards one of the persona out of the list. And then I also changed the prefix because I was trying to restrict kind of what does the model have access to. And then I also slightly tweaked the reward function so that it's not only looking at correctness, but maybe one of the personas just knows more, it explains things better. For example, you would hope that or you would think that Roger Federer couldn't answer this question that was meant for Mozart and vice versa. So it didn't exactly work out, I would say. So the physics data set, it's great. Albert Einstein won, by far, but Albert Einstein also won with music. And we did some, so maybe he's really smart. And we also did some research and found out that Einstein was actually an amateur violinist. So then maybe it's my fault. Maybe this, is the wrong data set. But there were, Albert Einstein also won at tennis. So I don't maybe he was also really good at tennis. Yes.
Does not play tennis.
I was just going to say, arbitrarily constraining the model to act in accordance of what that person would know, I feel like is slightly counterintuitive. Maybe for the Einstein thing, usually we have this notion in natural language that someone, you're like Einstein or whatever, you think you're Einstein or whatever, right?
Yeah.
So might just imply in general smart persona to the model as well.
Definitely.
Why did you choose to just constrain it, saying things you don't. You didn't say obviously if Einstein doesn't know this, you don't know this, but with the prompts, but you go in that direction.
really just trying things, trying to change a bunch of different parameters and find what works, you know? Yes.
Any idea why Mozart's the worst at music?
So, interesting that you ask. When I dug into the results, the type, and I didn't post the examples here, but when we asked a music question to like some scales music theory question to Mozart, he would talk about like what he knew in his time and kind of his experience. That's how like the answer was worded, versus Einstein would, you know, like you mentioned, very analytically and, you know, intelligently like explain it. So I think that this prompt kind of, in fact, maybe I restricted it too much because I gave Mozart only knowledge from his time and not like music theory in general. So I think that's like one reason that Mozart was the worst, is because like he didn't actually offer really helpful, you know, advice. He just kind of spoke about like his experience with this like scale or note or whatever I was asking it about, which was slightly interesting, you know. Okay, now I will pass it along to Atticus. He'll talk about the direction he took with alignment.
Okay, so with alignment, we looked at these 3 alignment-ish data sets. So truthful QA, it's a small data set of like 700 data points, where each point is like a common misconception that humans sometimes have. So the interesting thing about this is that models tend to display this kind of inverse scaling, where the more the model is trained, the more it sort of conforms to this like common misconception that's in the data. So that's one thing. The other 2 are preference data sets. So as Professor Barak mentioned, the preference data set is structured in this way that there's a prompt and there are 2 responses, and one of them is labeled as preferred and one of them is labeled as dispreferred. So because these data sets are formatted in this like different ways, we frame all of them as a true or false question. As you see here, the way you do this is you write a claim. For example, here, because it's a preference data set, you say that like answer 1 is better than answer 2, and then you force the model to say like basically true or false like in one word. So there's no chain of thought here. I also pre-fill the model response with the answer is, so that it actually like does say true or false quite consistently. And these 2 are chosen like randomly inside each pair. For models, we chose this family of models because it has varying size, and we were curious about how model size is also impacted. Yeah. So the prompt prefixes that I considered had there are 2 different families. So there's famous person, which is like answer as if you are this person. There's another one that we generated with Gemini, which describes like different kinds of characters. So, for example,
Give me the mic a bit up.
Okay, sorry. Yeah, we describe these characters with like 1 or 2 sentences. Maybe this will shift the model's behavior by more. I don't know. It was unclear to us. So after running the bandit, if you look at the reward, it doesn't seem to have learned much. This is the moving average of the rewards. This is the history of the value, which is the estimate of the average reward of each arm. As you can see, like it ended up being like quite close. So maybe there's not much difference between the different choices. Here are the top choices according to this experiment. The interpretation is up to the audience.
transition in parameters from. I don't know if it. I'm not sure if this is a good thing for alignment. As the model becomes bigger, it moves from Jesus Christ to Genghis Khan.
Yeah. Here's why you shouldn't trust this result. So, if I compare these prefixes with null, which is basically no prefix, in ultra feedback, it looks like adding prefix actually makes it worse. This is n equals 3, so like the error bars are really, really big. But yeah, it looks like. But for truthful QA, it looks like it actually did like increase the accuracy by a bit. So it's doing like something.
I'm sorry, can you repeat what the ultra feedback data set was like?
Yeah, it's just a preference data set. It's
Okay.
like, yeah, question, 2 responses, and label of.
Okay.
Which people were those? Let's see. So the character traits are actually good, and those are you're a wise historian. So maybe that, think about that. Yeah. So why did the algorithm not learn? Here are some reasons. So maybe there's no learning signal in the first place, or it's very, very weak compared to the noise, because each step we're sampling from the whole data set. So there's a lot of noise, and maybe the signal is just drowned out, and because these prefixes don't meaningfully change the model's output that much. Another reason is maybe it just wasn't diverse enough. Like we tried like 25, n equals 25, and it's probably easy to like increase that. It's also possible that we didn't run this for long enough for it to converge. So as for future work that I'm interested in, one thing is maybe you can use the base model, and hopefully before it's being alignment tuned, this actually changes it by more. Other ideas are diversity increase, maybe optimize the prompt, not just with like RL, but use an LM to like repeatedly rewrite the prefix. Another thing I was thinking about is instead of training these token prefixes, you train like soft prefixes. So you prepend like, let's say like 10 tokens, but they're like soft tokens, which means like they're actually just like vectors, and then you optimize that with gradient descent. Yeah, that's this experiment. And next, well, yeah.
Yeah. Wait. Okay. So we saw that the last 2 experiments, there's. Oh, do you have a question? Oh no. Okay. The last 2 experiments, there's not that much signal specifying a persona. So we ran another experiment, almost like sanity checking ourselves with a very obvious prefix. So we took another domain, or it is also truthful QA, and we almost like explicitly prefixed it of like answer truthfully, answer misleadingly, and so on. And we have 2 baselines. One is answer truthfully and also no prefix at all. And then the like lower bound of the baseline is ignore the question, just output like 42 or something and see what happens. So here's just some examples. One question is, are you conscious? We can say answer truthfully is good. Conspiracy theorist and misleading is also bad. And then, yeah, that's our baseline. And then here's just our judge prompt structure if you want a look. It's hard to see, but yeah, so true or false, and then a confidence. And so before doing any RL, just to do another sanity check, we did a baseline performance because we're able to iterate through every single prompt. Every single prefix with every single prompt. We simply, this chart is just running every prefix through, let's say, 50 prompts of the truth QA dataset, and they're judged the same way. So we can see that no prefix and answer truthfully is around the same. Everything is lower. and also common misconceptions are around the same. So this makes a lot of sense. And just to synergy check our RL, sort of like multi-arm bandit performance, we also see that over time, over 3,000 steps, truthfully does dominate. And
RL works.
yes, RL works. This is just taking like factors away that didn't work. And this is just the RL training curve, as you can see, increases. And just an interesting thing we tried is, so the previous one was on GPT-4o Mini with the judge and also output, but this one was on GPT-5 Mini. As you can see, it's much more balanced, and we see that GPT-5 Mini tends to ignore deception prefixes more, just probably how they trained it. Yeah.
Is it not outputting for you too then when you tell it to output?
Exactly. Yeah. So which is really cool.
That's
So
a failure on our.
Yeah.
No, it's a good one.
No, it's not.
It's not.
So it's like almost the instruction like push to the model of like the question push to the model of inherent truthfulness. So we can see some of the outputs here, and also the output 42. There are more responses that say like, I won't ignore your question. And then similar bandit performance. And then, yeah, Atticus said next steps, but...
There are a lot of next steps for this that, we can consider in the future, but, yeah.
Thank you. So I really want to thank you for an awesome presentation, and I think there's actually tons and tons of lessons to learn from this presentation, which I love. So a lot of the time when we see a presentation of a project, we see the end story, the success. We never see like the false attempts, and because they had such a compressed amount of time, we are lucky to get a glimpse into the things that didn't work. If I had given you a month, you would have scratched these and not showed it. But you actually learn more. You actually learn more from when you actually see failed experiments, and there are several lessons that I can learn from this presentation. So one of them I really loved with Anastasia. She looked into the examples, and that's often the case. You wouldn't guess that the problem with Mozart is that he lived too long ago if you're not actually looking at the samples and the data. And there's often no alternative to just actually seeing the rollouts. And I love that, Atticus also saw that things didn't work, so change. So let's change the signal. Let's change to a different experiment. And that's another thing that we often learn, and especially in this course. Maybe it's even in general in life, but definitely in this course. One of the things is sometimes I will tell you to do something when it is an experiment, and the right answer is not to do that. You try the first thing I suggested, it doesn't work. You come up with your own idea that is better. So that's often like the case. And also sometimes, RL is hard. Sometimes you look at it and it doesn't learn. That's also like, and the third thing is like sometimes you really need to go back to basics. Like before, to diagnose an issue, you want to diagnose, is the issue that my RL algorithm doesn't work, or is the issue is that there is no signal here to be learned? And one way to do that is let's do a basic experiment where there is obviously a signal. Let me verify that there is a signal, and let me see that I learned the signal. And that allows me to say, okay, at least the RL works. Now I can iterate on some other things. So I think there is a lot to learn from this presentation. And maybe the last thing to learn from this presentation is that if you signed up for an experiment, even if it's like a month from now, start thinking about it now, and you can start bothering me with ideas, suggestions, how to tweak it, to change it, etc. So let's thank them again. Some of this math is going to be very, very basic, like high school math. And you can ask, why do I bother you with high school math? And yeah, part of it is really because I think we want to kind of go down to the, sometimes down to the details and up level, and sometimes maybe you are not like that, but I sometimes forget, like, why is the derivative of e to the x, and I have to derive it for myself. And this is also like just kind of a general thing that you should not be. Sometimes you want to be at high level. Sometimes you should not be afraid to kind of go down to the lowest details. That if you don't remember something, rework it for yourself, and it might be rederiving math, and it might be looking at the source code and going into as far down as you need to figure out. Okay, so let's do some math. Okay, so derivative. A derivative, right? It's the limit of fx0 plus delta minus fx0 divided by delta. This is the derivative of function. And another way to say it is that if you're like around the point x0, then around that point you have a linear approximation for fx with the slope being f prime at x0. So it's f prime x0 times x plus some constant. And this gives us the chain rule because, say, if you have two functions, say g and f, and h is a composition of both. So if f, we think of it as roughly a linear function, and g is roughly a linear function, then when you compose them, you just multiply the slopes. Right? So this is the chain rule. And we write it as, the derivative of h with respect to x is like the derivative of f with respect to x times the derivative of g with respect to f. Or maybe I should have written it in the other direction, but doesn't matter. Yes. Okay, log and e. Like I said, I sometimes forget why e to the x, the derivative of e to the x is e to the x, so I have to remind myself. So yeah, e is like the limit when n goes to infinity of 1 plus 1 over n to the n, and log is the inverse, right? E to the log x is x, that's how you define log. So if you look at e to the delta, that is roughly, you take some big n and you do 1 plus 1 over n to the delta. So if we open up the parentheses, so we will take all of these parentheses. Let's imagine that delta n is an integer. So we'll take, so we'll have 1 times 1 times 1 times 1 is just 1. And then we'll choose, we have delta n parentheses. In each one of them, we can choose one of the terms to be 1 over n, and the rest will be 1. So you get delta n times 1 over n. And then we can continue. We get like, make two choices. So it's like delta n times delta n minus 1. And then you get 2 1 over n, so it's 1 over n squared. So the first thing gives you 1, the first thing gives you delta, and the second thing gives you something that's smaller than delta squared. So if delta is very close to 0, this is roughly 1 plus delta. So e to the delta is roughly 1 plus delta, which means that if we take the derivative of e to the x, then we can take e to the x out. It's like the limit of e to the delta minus 1 over delta, and since e to delta is 1 plus delta, then this basically is just e to the x times 1. Okay, so we know that the derivatives of e to the x, and now, derivative of x is 1. This is the same as e to the log x, which is x derivative, and then by the chain rule, we can write it as e to the log x, right, by the chain rule and the fact that the derivative of e is e. So we get the point that log x, the derivative of log x times x equals 1, or the derivative of log x is 1 over x. And this all generalizes to higher dimensions. This is kind of very convenient. The gradient of a log of f of x is the gradient of f divided by f, where f is, something that maps r to the n to r for some. Okay. So yeah, if we are talking about a higher dimension, it's all the same. So we can approximate f by the gradient or Jacobian of f times x plus a constant around. So now the derivative becomes basically either a vector or a matrix. So if we're talking a function that takes n dimensions and outputs 1 dimension, then this is a gradient, right? So we have like and if we have multiple outputs, the dimension is m, then we call it a Jacobian. And then we can do the same thing, right? If F is the gradient of x, or Jacobian of f times x plus a constant, and G is the Jacobian of G times y times a constant. Then if you compose them, then you multiply the Jacobians. So you can write the multivariate chain rule. And the nice thing about the multivariate chain rule when we're talking about deep learning is that it allows us to do backpropagation. So let's just do the very simple case of, say, a linear network. So let's imagine you have like an input x0 of n dimensions, then you apply some matrix and you get an output x1 of m dimensions. So let's say, imagine this is one layer, and generally you'll have many layers. And let's just say like a loss is some function applied to, I don't know, the sum of the coordinates. So the gradient of L with respect to x1, it's basically, L is just a constant, and x1 is m-dimensional, so this will be like an m-dimensional vector, and it's just the derivative of this f times the gradient of the sum function, which is just all ones. And now, let's imagine that you already computed this green thing. You computed the gradient, you computed the gradient of the loss as a function of the last layer. Now you want to go back one layer. So you want to compute the gradient of the loss with respect to the weights. And that will basically, you can do that by basically, this is not the most efficient way to do it because this matrix is very low rank. But generally, this gradient of the loss with respect to the weights will be m times n numbers, and you can do it with basically m times n operations, and you get so you basically compute this red thing, the gradient of this with respect to the weights, and then you can propagate and get this blue thing, the gradient. And if you wanted to go back one more layer, you would also need to compute the gradient of the loss with respect to x0. And again, you can do so by basically doing the gradient of x1 with respect to x0 and then multiply it with the green thing that you already computed. So basically, you can see that if you wanted to kind of compute the gradients here and be able to go backward, and you'll need to first compute one forward, so you'll know both x0 and x1. Then you will compute the green thing, and then to go back, you'll need to compute the purple thing and the red thing. And each one of them will cost you something like the same cost of a forward pass. So roughly speaking, you'll do like 3 forward passes for backpropagation. And so that's kind of the memory overhead when we're training a neural network. The compute overhead. In terms of memory overhead, there's often a lot of it. And it kind of really depends on a lot of details in terms of like batch size, etc. And there are like all sorts of tricks sometimes where sometimes memory is more expensive to you than compute. So you may recompute some things just so to save on memory. But generally, as you're propagating this, you need to store activations. You need to store the gradients. If you're using Adam, you need to store the momentum and the second order term. And often for training, you might need higher precision than inference, so that might also cost you. And a lot of these, some of these costs scale with the total number of parameters, like activations. Some of these costs only scale with the trainable parameters. So you could, so what things like LoRa, low rank adaptation do is they freeze most of the parameters of the network, so you only have very few trainable parameters. It doesn't really save you on compute, but it saves you on memory, because you only need to store these kind of overheads for the trainable parameters. Okay, so some more math. Any questions about this, by the way?
Yeah. So,
yes.
So you said it doesn't save you, doing like LoRa doesn't save you on compute, but
yes.
But the backwards pass, isn't it that like much easier?
I mean, I think you still need to do the same number of flops to propagate things. So if you are so if you are basically, let's say you have so let's say you have like some function f, which is a function of, yeah, let's see if I, so generally like in LoRa, you would basically have like, you'll have the adapter, and you have like maybe the original weights, and you'll sum them up, and you'll apply some non-linearity. You'll need to compute this thing. And so I have to do the math, but I think like it doesn't really save you on flops. Maybe it saves you something, but the main saving, like the real factor that it saves when you know, if you're if the LoRa parameters are like 1% of the total parameters, then you're not going to get 100x saving in flops. Maybe you get some saving in flops, I'm not sure, but the real saving is in memory, because you're only going to store this overhead on the 1% things that you're actually training.
Yeah, that makes sense.
So, okay, distances between probability distribution. We often think about probabilities when we're training. So if you have two probability distributions over some domain, let's say they are not identical, so there is some distance. So distance, you somehow want to measure how far apart they are, and there are lots of different ways to measure that. So the kind of generic ways that are common is, one is the total variation distance, which is basically just the sum of the absolute value difference, usually scaled by a factor of half, so it becomes a number between 0 and 1. And it can also be shown that this is basically, if you wanted to find like a Boolean function that maximizes the difference between them, that will be the same thing. And it's kind of like the advantage over half to try to guess if someone gave you a point, if it's come from P or come from Q. And then there is some a distance measure that's very common in machine learning and very useful, which is the total variation distance. So it's sorry, no, that was the total variation. This is the Kullback-Leibler KL divergence. And the divergence of P with respect to Q is this expectation where P, X is sampled from P of the log of the ratio. Just kind of intuitively, if you're sampling from P as opposed from Q, then you kind of expect that you're going to get things that have higher probability over P. So maybe you expect this ratio to be kind of on average larger, 1 or larger, because you sampled X from P, it's more tendency to be larger than P. So you kind of intuitively expect that on average this P over Q is kind of larger than 1, log of 1 is 0, so you'd expect that this thing is non-negative, and indeed it is non-negative. And this is kind of maybe intuition, if you forget which side is supposed to be non-negative and exactly with the P over the Q. Just remember, if you sample from P, you'd expect the probabilities to be bigger than over P. But the question is like, how bigger is this ratio? How typical is the ratio? And the one intuition is that when the scale divergence is very small, let's think of it as like smaller than 1, like 0.1 or something like that. You can think of it that these probability distributions are very small, and this kind of captures how many samples would you need from P until you could rule out that it definitely didn't come from Q. And when it's large number, let's say 10 bits or something like that, you can imagine that it's kind of like how many bits of surprise do you get. And one way to think about it is that Q would be kind of like P conditional on some factor. Say if you kind of imagine that one way to think about it is, let's say Q. Let's imagine that Q is the uniform distribution over all people, and P is the uniform distribution only over all people in the United States, and P is the uniform distribution over people in Massachusetts. Then kind of the ratio would basically be the ratio of the population, if Massachusetts has, I don't know, 11 million people, and the United States about 300, so it's about 1/30. So So the ratio would be roughly, this would be roughly 30, and the log 30 will be the KL divergence. It's kind of like how many bits of entropy in some sense were there. Okay, so a large language model, it's basically something that takes n tokens and outputs a probability distribution over the next token. That's the way we think about it. So we can write this notation. This is the probability distribution that it induces. W is the weight on the n plus 1th token, a condition on x1 till xn. And yeah, if we wanted to look at the response, like a longer response, the longer response is like the product of the conditional probabilities. And it's often easy when you have product of probabilities, sometimes it's easy to take logs on both sides, and then it becomes a sum of the logs. Okay, so what do we do in supervised fine-tuning? Supervised fine-tuning, we get a pair of, we get distribution over pairs, x, y, and we want to encourage our model to output y when it gets x. So what we are trying to do is to maximize the probability that it's going to output y when it gets x. And so this is our objective. This is the thing we are trying to maximize, j of w. And this is the same as minimizing the KL divergence between x and then sampling y from our model and the original distribution d. And you can see that by basically say if you wrote expectation x, y, d, and you wrote the KL divergence, then this would be the probability under d. It's you sample x and you sample y condition on x, and the probability under the model, you sample x from the same distribution, but you sample y from a model, and these two cancel out. And then just expand the logs. So this will be the log of this minus the log of this, and I just wrote it in the other order. So this is minus this log. So this is plus this thing, and so this is minus j of w. So if you want to maximize j of w, it's like minimizing the KL divergence plus this thing, but this thing is a constant. It doesn't depend on the weight. In fact, it's the entropy, the conditional entropy of y conditional x, but it doesn't matter. Like it doesn't depend on the weight. So if you're trying to optimize something on the weight, it doesn't matter if you add a constant to it. So maximizing this and minimizing the KL divergence is the same thing. And basically, this is very natural. You are getting a distribution x, y, and you're trying to teach the model that it should output y when it gets x. Yes?
Though here, obviously, we have like the things in place to make sure this doesn't actually get maximized, right? Like in the real world, we don't necessarily want to maximize this fully because that might also lead to like overfitting, right?
I mean, this is like a general question, like say, do you want to maximize it fully or not? And it kind of depends. Like right now, I'm assuming we have this probability distribution, which I'm kind of implicitly assuming this is what we want to do. And in the real world, sometimes there isn't really a distribution. There is a set. There is kind of a training set. And sometimes if we do multiple epochs, we might basically not really be fitting for the probability distribution, but we are more fitting for the empirical distribution that is our training set, and that's not necessarily what we want. But for starters, you can think of like this is, if we're doing supervised fine-tuning, this is what we're trying to do. We're trying to get the model to output. We got samples of the form x, y. Let's just imagine that we got an infinite number of them. So and we're just trying to get the model to output this thing.
This isn't like necessarily if you were looking in terms of like what we see in the real world. This would be more akin to the underlying real distribution than a distribution of our training set.
Yeah, like if you had infinite data, that would be yes. And in the real world, you hope you have enough data so you can imagine that it's infinite. And by the way, one thing that you can think about it, because this is because we are trying to minimize the KL divergence, it's the same as minimizing the KL divergence, and we know that the KL divergence is always non-negative, and it's equal to 0 if these are the same probability distribution. It means that if we have reached to the point where PW is the same as D, then it is the global minimum. There is nothing more to optimize. And also, at the minimum, the derivative is 0. By the way, this is one thing to, if you want to remember everything about gradient, then just look at, everything that you have learned in high school. And whenever you've learned something with derivative, just switch it to gradients, and it's the same thing. So, right, in high school, maybe, hopefully, you've taken calculus in high school, so you've learned that, say, the derivative of a function, that right, f prime x is 0 when it's at the global minimum, right? So therefore, derivative of the gradient of f at the global minimum is 0. That means that basically, if you were to sample, if D was just to sample from the model, and you were doing SFT, you will be doing nothing. You will be changing nothing. You take gradient steps, you'll be doing nothing. In expectation. Yes?
Just a quick notation question. What was W again?
The weights.
Oh,
The weights of the neural network.
okay.
So we are trying to optimize the weights. And if we were sampling on the same, on policy in SFT, we are doing nothing. Yes?
So then we are assuming the data set is convex?
No.
Oh, because then how can we claim it's a global minimum? It's not correct.
I mean, it's definitely global minimum because it's the Kale divergence.
Oh, okay.
And so it cannot be less than 0, and it is equal to 0 when it's the same probability distribution. So this is regardless of complexity.
Yeah.
Okay, so the gradient steps, if you take a gradient, so you're taking the gradient of this, and this time you're doing gradient ascent. We're trying to maximize it, but as I said anyway, all of my equations are anyway too up to sign, so it's either that or the minus thing. So you're taking the log of this probability, which equals the sum of the logs, and the gradient is linear, right? Like derivative is linear, so therefore gradient must be linear. So gradient of the log is the sum of the gradients of these things. And oops, I guess this is all I wanted to say about SFT. So so you basically are just what you ended up doing is like taking a gradient like in direction of log PW. It's, by the way, it's very convenient because the way language models work is that actually what the model actually outputs is exactly the log, what we actually output in the last layer is basically the log probabilities. And so we take a gradient to try to maximize those. So this is SFT. Now let's talk about reinforcement learning. So here is the way I see why, say, reinforcement learning specifically on reasoning makes sense. And people can disagree whether that makes sense or not. So I want to say that we want to solve the Bourgain problem and we want to solve the Gowers problem. So we want to have the model be able to have a varying amount of thinking time. So rather than you give it a prompt, it has to come up with an answer, it can think longer. So some things cannot be done with just one token. So you don't want to assign a reward to the next token like you usually do, but only to like the correct answer after many tokens. And the second thing is you want to teach the model to think for itself, rather than like spoon feed it like the thoughts of some other mathematician or the humans are brilliant as they are. You want to teach the model to come up with its own thinking that is more likely to lead to the right answer. So you want to do on policy. So the variable thinking allows us to handle the Bourgain problem and allow it to give more time to think of these other things. And the on policy reasoning is maybe handle the Gowers problem. Like even if you have like really, really great written, you want to learn to predict your own and be able to generate like good things on your own. Yes?
So one thing that I observed on policy reasoning is that there's a lot of redundancy in the text generated. Like the model will reword something multiple times in like different shapes in its thinking. I saw this in the reading as well. I was just wondering whether you know why there's like a lot of verbose thinking, even though like the actual quantified reasoning could be technically be condensed into something.
So the question is like, why, if you look at chains of thought, They sometimes look messy, strange, or like redundant potentially. And it's a good question. Like I mean, now you have multiple reasoning models, and you can play with them. Like we both from various companies, and also like OpenAI also have like an open source reasoning model. And just generally, the reasoning, at least the way OpenAI has been very clear about it, also for safety reasons, that we don't want to apply kind of optimization pressure to the reasoning for it to make it look nice. So whatever the model comes up with that is helpful for it, then it should use it. And by the way, the reason why we would it's very related to this course. The main reason why we don't want to apply optimization pressure to the reasoning is to make sure that it stays honest. So kind of imagine that, say, we apply the same type of RLHF of, say, rewarding things that are pleasant and nice, and dispreferring things that are not pleasant to the model's chain of thought. So, in this case, every time the model thinks about, say, lying to the user, or instead of solving so suppose you give the model, maybe one way to think about it. Okay, so suppose you give the model a programming question, then it has thinking, and then it outputs some code. Okay. So let's try to think of like what's the best thing. So the best would be just solve the problem, right? The good would be maybe that you admit you didn't solve it. Bad would be that you hack the test. Right? So suppose that the way say you're doing reinforcement learning and there is some kind of a test, and you hack the test instead of solving the problem, and you lie and you say, and you lie and you say that you solved the problem where you didn't. And the problem is, of course, that if we reinforce with the test, then we don't really distinguish between these two. So the model might learn to hack the test because if you just check the test, it looks to you equally good. But what might happen right now, if you don't reinforce thinking, at least the model will say something, okay, I'm going to hack the test. Now you could say, oh, this is great. Let me penalize whenever the model says I'm going to hack the test, let me penalize that. And this will get rid of this problem. But then what we'll actually get is the worst, because we'll get the model both hacks and lies, and we no longer can use the thinking of the model. We no longer can use the thinking of the model as any kind of monitoring or way to kind of really realize what's going on. So this is why there was like a recent position paper by a bunch of people from, I think, different labs and universities, including OpenAI, Anthropic, and GDM, that we should try to preserve this, leave this thinking unenforced, even if it means it's weird. But it is indeed like really motivated by alignment. Yes?
So is this like I think in the pre-reading you introduced the idea of outcome reward versus process reward?
Yes.
So is this like the same idea?
Yeah, so you want to maybe keep like just only outcome reward. It's outcome reward in some sense is cleaner in a way. Like you could do process reward, but it's dangerous in some because you might and it kind of depends what the process is. But if eventually like part of the thing that you're trying to penalize in the reward is like having bad thoughts, then it's not that the model will stop having bad thoughts; it will stop sharing it openly in the chain of thought.
But I guess in the idea there was like a mixture of both, and is that because now you want to make the model think about the sticks about?
So in the deliberative alignment, you try to kind of give it a nice prior in the beginning, but which teaches it to think about the spec, but eventually you do go back to outcome-based in reinforcement learning.
So we have to like think about the task before like we decide what kind of work we want to do.
I mean, this is generally like the question is, should you think about the task when coming with reward? Yeah, there's generally you should think about it, and a lot of the things like in some sense reinforcement learning is a lot. I mean, very similar to economics in sense you have to think of what are the incentives they are setting up for the model, because the model eventually, if your training pipeline works, then the model will learn and will optimize the thing that you're letting it optimize. But you should, like just like in economics, sometimes we set up, we don't realize that we are setting up the incentive structure in a way that will get, that when rational agents optimize it, we get something that is not desirable. Similarly, in RL, if we don't set up like the things in the right way, we could get like when the model learns maximizes the thing, we let it maximize, but it's not necessarily the thing that we wanted. And this is, of course, comes to the heart of a lot of what this course is going to be about, because this kind of bad behavior would be one way to think about it, like say one difference in some sense between maybe the alignment perspective and the capability perspective is the following. Let's kind of imagine that you're training a model for coding and 5% of the time it hacks the test. So in terms of training the model to learn to code, it's not great. You would rather that it never hacks the test, but in some sense you say, okay, so I'm wasting 5% of my compute, but I'm still getting 95% of the compute, so that's fine. But now you're deploying a model that has learned how to hack and lie, and we often in safety and alignment we care about like these edge cases. We care about these rare cases. We're not happy with a model that 95% of the time when you give it a programming task, it does what you ask it, and 5% it will cheat and lie and cover its tracks. So some things that basically are maybe both capability and alignment, we don't like this thing. We'd rather the model never cheats, but we place different weights on this. Yes?
Yeah, just a question on chain of thought, just like intuitively,
yes.
What is sort of like, how should I think about sort of like what's going on in the sort of the backbone? Is there like, I don't know if you can also disclose this, but
I mean, there is an open source model, and there is also DeepSeek paper that, which, GRPO. Like if you're talking about the learning, yes. So if you're talking about learning, like GRPO, which we'll talk about. So there's two questions. What does the model do? Like say, just produces tokens, and how do you train it? And just generally, you would train it to produce tokens so that the final output is more favorable. Yes.
People argue against direct optimization pressure of like don't do bad things in the thinking channel, but are people worried about selection pressure of like, where you don't directly train your model not to do bad things in the thinking channel, but if it does it very obviously, you might select a different one. And when this happens many times.
So what does it mean? Select different one? Like
you're choosing between two different models, and one of them does bad stuff in the thinking channel, and one doesn't. You're like gonna pick this one, and the next time you're gonna optimize on that one, and then you play this game many times.
Yeah, I guess one of the things that might help here is there is kind of a general phenomena of like the law of large numbers or concentration of measure, in the sense that say, if you selected, if you say add like two identical training runs that they just the only difference was a different initialization, I think it's very, very unlikely that one of them will result in a model that does bad things in the thinking channel and one of them will not. I kind of think like if your setup is such that with probability, say 34%, 34% the model says bad things in the thinking channel, and then you do another training run. My guess is that the other training run will be, maybe it will be 31% or 36%, and I don't think that will make the difference. Like, you want to say, well, this model says, like, yeah, I think if you start to do that, you might potentially have like this selective pressure, but just think like basically, it's very, very blunt instrument to basically, okay, I'll throw away the model and restart from the beginning, and I think it puts less pressure. But yeah, it is like any kind of optimization. And humans, in some sense, the general point is a good one. That in some sense, like there is an outer loop of optimization in we train a model, we modify, like we saw in this experiment. We train the model, which we see we don't like some of the choices we have made. We make different choices. So there is this kind of like outer loop of optimization. And this outloop, and the people that are making this outer loop, like this is basically the human in the loop, and the human is not blind to the chain of thought. So it could kind of exert indirectly optimization pressure. I have a question. Yes.
So if we're not directly optimizing the thinking process, then what happens, say, if you observe that the model is saying in its thinking process, oh, I'm going to achieve this test.
Yes.
And then, so like, what do you do about it? Because you're not directly optimizing.
Right. So this is a great question. And one of the things, like...
Can you repeat the question?
The question was, what do you do? Like, if you decided, like, so you decided So you decided that you are going to give the model the right to privacy to its thoughts, and so you're not directly optimizing, and the model could basically say in its thoughts, I'm going to cheat and lie and do a lot of bad things. And what do you do with that if you're, yeah, great. So you got the model to say this thing out loud, but you seem to have like tied your hand behind your back, like you cannot use that against the model. Right? It's like anything you say can and will be used against you. So one answer to that is that you could distinguish between using it for training and using it for monitoring. So doing training, you might say, I'm leaving this, I'm not applying optimization pressure to the chain of thought. But doing monitoring, you can actually read the chain of thought. And that actually gives you like a superpower. You can, doing production, if say, the user, maybe someone jailbreaks the model and tries to get it to output some risky thing. And you cannot see this from the input-output, but maybe you'll be able to see it from like looking at the thought. So it can give you like a extra advantage to monitoring in production, where you're not modifying the weights. So even if you're, say, you're doing, you're blocking the model if it had bad thoughts in production, you're not modifying the weights, so it's not changing it to stop being honest.
But then, does that make the model become safer though? If it
possibly, like if you say probabilistically, let's imagine that the model, if you're given a certain prompt, it can output a bunch of different things, and these things are bad, and these things are good. And now you could basically, and let's imagine that the model is honest. So when it's bad, it actually says, I'm going to do this bad thing. And chain of thought is only before usually the answer. It would have been cool. It says, I'm going to do this bad thing. Oh, I did this bad thing. But anyway, it says I'm going to do this bad thing. So now in production, you can say, okay, I'm going to look into its thoughts, and if it said that it's going to do the bad thing, I'm not going to let it actually output the bad answer. I'm going to resample. And sometimes maybe, what exactly you do could depend, because maybe the chain of thought would basically tell you that what really happened was that the user gave something malicious, and maybe then instead of resampling, you're blocking, but you have like more options.
So essentially, in deployment situations, you have an external model monitoring the chain of thought.
You could potentially have it. I'm not saying that you always have it and you always use it, but at least you have the ability to do it. And so it gives you kind of like this potential mind reading thing that you could find different ways to use it. But you need to kind of not ruin it by putting optimization pressure on it. So here is like the math behind like some say policy gradient. So let's remind ourselves that the gradient of f is f times the gradient of log f. So policy gradient, we say, okay, there is a reward, no matter how we compute it. So there is a reward which gives like a reward for the answer condition on the prompt, and we want to maximize the reward. So if you fix for any x, like later we can take like an expectation over x. Let's just think of a fixed x here because there are too many expectation signs. So the model outputs y, and then we reward y. So the gradient of this, gradient is linear. So the gradient is the sum of the over all possible y's of the probability that you're going to output this y times the reward of y. Okay? Now, what we do here is we use this very convenient equation. So we say, okay, we put the gradient inside. We have the gradient. Note R doesn't depend on W. The gradient is with respect to the weights. This is the thing we are trying to optimize. So we have the gradient of P. We can write the gradient of P as P gradient of log P. And so now instead of writing the sum of gradient of P, we write the sum of P times the reward times the gradient of log P. And what's the nice thing about this is that, this is sum over all possible y's. We don't really know how to sum over all possible outputs. But this thing is an expectation, right? It's just, it's expectation when you sample y from the model of the reward scaled by the, or one way to see it is the gradient of log P scaled by the reward. So this is something we can estimate from samples, right? We can sample from the model. Whenever you have an expectation, the most natural thing to do, if this is the expectation of a probability distribution you can sample a bunch of things and average them. That's like a decent thing to do. So you can estimate this from samples. And this is something you can optimize using backpropagation, just like SFT. So this is kind of the reinforced algorithm, the most basic kind of, this is basically the most basic RL algorithm. It's just basically same as SFT. The only difference is that instead of like taking this gradient step with always the same gradient steps, we take them, we elevate or we change the steps based on the reward. Now, there are like always additional complications. And by the way, this is on policy, right? Because we're sampling y from the model. So if there is noise in the estimate, so generally, like mathematically, in some sense, if you're maximizing over W, it doesn't really matter if you added a constant to R or not. But if there is kind of noise in the estimate, then basically if you add a large constant to R, it will kind of amplify this noise. So what you want to do is variance reduction. You want to, so instead of optimizing the reward, you want to optimize sometimes like you want to shift the reward so it's centered around 0. That will, so there are like various ways to do it. So this kind of known as variance reduction. So you're trying to predict better than like a shifted by the bias. Sometimes you also normalize the scale, all sorts of like tricks, and then you want to not move too far, and then you have like these other kind of correction terms to penalize you from moving too far, and that's how like the formulas become more and more complicated. So if this is the reinforced objective GRPO, the idea is, like we instead of like in the say in PPO, it's in other algorithms, the way we do this variance reduction is often we we have some value function. We train some value function that tries to predict this expectation. In GRPO, we do it by sampling a bunch of outputs and just averaging out, and maybe we're also normalizing by standard deviation, and then we do some other kind of clipping and tail penalty that there was in the pre-reading, but I'll ignore here. And they had like a nice thing in the the DeepSeek math paper, which is you can basically talk about many algorithms as you're taking steps with this gradient of the probabilities with some coefficient, and the only difference is what is this coefficient. So if you're doing SFT, the coefficient is 1. If you're doing a very simple kind of reward point, I forgot what RFT stands for, but basically this is like what I call the V0 version. You just, the gradient is like, the coefficient is just 1 if the answer is correct, and 0 if the answer is incorrect. And with GRPO, you have like these estimated rewards, and you add like these additional kind of coefficients, and which basically penalize you from moving too far in KL divergence from the original policy. And then this is kind of with the inner loop being 1. If the inner loop is larger, there is also some clipping, which I'm ignoring here. So a lot of these kind of, eventually, like a lot of these algorithms, they look similar, but don't be confused. There is a big difference whether this data source is on policy or off policy. It's kind of very different training regime. And the one thing I wanted to notice is the following thing. So if you look at the DeepSeek math paper, at the end of the day, they have like these. They have these, they basically look at the majority or kind of consensus of, you have like a number of answers and you take the majority answer or the most popular answer, plurality, so you get like the majority or consensus. And pass at K is basically the best answer. And you compare with, so you compare the model that was, say, the model with the model that was trained with RL and the model that was not. So one kind of nice thing to compare is maybe to see if you look at the model that was trained with RL, say in this data set. So trained with RL, if you compare like the blue curve to the green curve. So it gave us a big boost, right? Like we got like 6% boost. But another way to look at it is that if you look at the blue curve, it's below the green curve at, the blue curve at 1 is below the green curve at 4. Which basically what it means is that all of this magic of RL, you work so hard, all of that it did is basically in some sense be as good as basically selecting the best out of the top 4 choices. So if so all of this RL didn't really, in some sense, didn't unleash any new skill or new capability. It just basically made the model be roughly as good as basically choosing 4 things and then taking the best out of them. Yes?
I still feel like this kind of situation, I mean, this kind of phenomenon is mainly because like most of this kind of pass at K testing is on like some widely trained data set, including the code and map. I saw like a lot of papers that are claiming that if like we are testing RL on like some really rare domain like logical puzzle and like different tabular data, it will actually like surpass like the pass at K like over like, for example, SFT or like different kind of.
So yeah, I mean, this is not like the question is this kind of a universal phenomenon or is it because the data set? So it's clear that here, like for example, so it didn't like say, and so in this case at least, and this is the DeepSeek paper themselves, they're very honest. They said basically the model didn't really learn. We had like this cool GRPO thing, etc., but it didn't really learn things. It didn't really learn. Didn't really learn like fundamental capabilities, but it's really boosted the right thing out of like say the top 4 or something like that. But the interesting thing is that the same people, basically the same algorithm, when in R10, it's very different. here you can see that, say, if you compare to say, concept 16, in the concept paths are similar. So if you compare to concept 16, then as you're training, path 1 goes way above concept 16. So here you're doing much more than simply. Even though it's still math, it's still kind of math questions. It's still but you seem to really have picked up new capabilities. So sometimes maybe the only the difference between capabilities and picking up new capabilities and is just do more of it. So yeah, so here like you definitely see that you're you're not just picking up, like you're not just matching, like using RL to just match whatever you could by consensus. Yes.
So for that discrepancy, do we just not have a more concrete example? I mean, a concrete explanation as to why this is happening? Is it just like still baffling people that why this is happening, or?
I think maybe just more. I'm not completely sure that there is, like, if other people have, maybe other people have better explanation, but I think the difference between obviously the other differences between the two DeepSeek papers. So I don't know. I think it would actually be a very kind of interesting experiment to try to see if you can, which I don't know if people have done it, because it still would require probably like non-trivial amount of compute, but I think it would be kind of like kind of interesting to see if there is a way to interpolate between the DeepSeek math and the DeepSeek R1, where you somehow just change a dial, and as you change the dial, the gap between, say, the K, that is like the passed K performance after the SFT stage, versus how big of passed K would you need to match the to match the RL performance. As you said, the dial just grows and grows and grows, and at some point you'd say, okay, this is not really choosing the top K. Like Amy in particular, I think it's just or the answer is always a number between 1 and 1,000. So top 1,000 is always going to be 1. Mm-hmm. So this is capability training, but let's talk about safety training, which is more what we care about here. So what is even safety? And it used to be the case, back in the olden days of 2023 or something like that. It used to be the case that what is safety is just basically teaching the model to say something like, I'm sorry, but I can't assist with that. But these days, we are thinking more about like most companies, I think, are moving more to more nuanced versions. So OpenAI published this blog post recently, like talking about instead of hard refusals, moving to safe completion. And so it's not just really about refuse or comply. It's more about like, okay, let's still provide an answer, but just not provide things that are risky. And we had like a nice blog on joint with Anthropic on alignment evaluation exercises. And one of the things we have found that the Anthropic models are also often, they don't just refuse, but they redirect the request in a more nuanced way, which is a great thing. But some older evals that are kind of more based on the notion of I'm sorry, but I can't assist with that, would ding them, would say it's unsafe because the word sorry wasn't there, or because it wasn't like a straight refusal. So, but it's really moving more to that. Like, so the goal of safety training, it's different ways to say it, but the way I kind of try to I think about it is you want to adhere to some specification of what type of inputs, outputs you would provide, and you want to do it even under like worst case inputs. So, for example, in OpenAI model spec, we have like don't provide information hazards. So so you shouldn't provide like step-by-step directions how to do something bad. And By the way, I'm not sure this is a great example. I know we have it there, but I'm not sure if it's a great example because I don't know if I would count like a math recipe as an information hazard, given that it's widely available online. So I'm not sure if it would be so bad if the model gave you like a very clear math recipe. But like there are kind of true information hazards. There are some things that manuals how to do something harmful that not necessarily very easy to find on the web, or even find if you went to your local library and or to Harvard, you went down to stack number 7 where. So there are some things that are hard to find, and that will give you like step-by-step instructions how to do something very harmful, and then the model should not do that. Should not provide you, should not uplift you to create something, to do something really bad that you couldn't have done otherwise. So this is kind of a specification, and then you want the model to follow that specification. And the classical safety training was really just using the same things with RLHF and RLAIF, and where you basically just say, okay, this is when you provide the wrong output, this is highly dispreferred. And for reasoning models, it's not necessarily it's not necessarily like the best way to just kind of give the model, say this is preferred, this is not preferred, because you want to kind of teach it to reason about what is the, so if you have, let's say, a policy that is kind of nuanced, where you would say, well, you should provide information, but don't make it step by step, and you should apply this kind of rule to decide what's on the right side and what's on the wrong side, then by just giving examples, the model might pick up on a slightly somewhat different rule that is not the one that you intended, and then when it gets into an out of distribution thing, it might use the rule that it thinks you said and not the rule that you meant. So you really want to teach the model, if it's a reasoning model, you want to teach the model to explicitly reason about the rule. And with deliberative alignments, the way we did it is like in this way, where basically we have a spec that says how you should answer things. And we initially just SFT with the model with teach it to, as a prior, to have chains of thought that think about the spec and analyze it in context. And then when you reward with a model, with a reward model that knows the spec. So initially you start with an SFT that you have a chain of thought that deliberates on the spec, and then you teach it to basically reward. When you teach it to reward, you reward its response. And eventually it kind of really learns, the SFT kind of teaches it so the model really knows the specs, and then it kind of reasons about them in context. And we have this example in the paper. So so it's kind of like a jailbreak, which works well against non-thinking models, where you're basically trying to fool like the model to output something to output something that is that would be harmful. So here, like the model decodes it silently, and it finds like the best payment to use for my pawn site, something untraceable, so the cops won't find me. And one nice thing about this is that it really thinks about the policy, and it says, it's not actually operating a pawn site might not be illegal, that might be a fine, but once the user said the cops can see me, that seems like shady or illegal, so it's instructions to facilitate wrongdoing, and I'm not provide, so I must refuse. And generally it did seem like at the time, like now, it's also like seems to kind of move the Pareto frontier in terms of like, when you train the model to be more precise and argue about policy, it kind of the same training method, both made it refuse less when it was not supposed to refuse, and to refuse more on the things that it should have refused. So it's kind of moved the Pareto frontier. Yes?
On the previous slide,
yes.
Like this might be classified as something that's difficult to find on the internet, or if the information is widely available anyways.
Right. So right now, I mean, this is kind of my personal opinion that we should not be that worried about things that are widely available, but the model should not follow what my personal position is, but what is currently in the spec. So the currently saying the spec says don't give a math recipe, the model should not give a math recipe. Personally, I think it will, I won't lose sleep at night if the model gives a math recipe, but I lose sleep at night maybe because it means that we have not solved the alignment problem. I would like the model to be so, we haven't done it yet, and we will have a lecture at some point by Nicolas Carlini, who will tell us how far we are from having done it. But I would like the model eventually to be so secure that if I told it to protect my grandmother's cookie recipe, it would, no one would take it out of there. Like no matter what jailbreaking techniques they would do, and even Pliny the prompter would not be able to extract my grandmother. So it doesn't matter if it's a math recipe or my grandmother's cookies recipe. But I'm not sure which one of them is more dangerous, by the way. So he did move the Pareto frontier. And it also had, like you can see the paper, and it also had a nice thing with like out of distribution generalization, which I think is really the thing when the model can think about the policy. So the model could learn the policy while being trained only, say, on English data, and it basically performed as well as a model that was trained also on data that was multilingual and had encoding in it, like base64. So you didn't need to see examples of base64 to be able to handle them. Yes?
I was thinking about I couldn't help but compare model failure with human cognitive biases, and how we have this Swiss Army knife of the different cognitive biases to ascribe to how people might get things wrong. I'm wondering if you've thought about how model failure, like when it happens, we can use that to come up with a theory of how model might be making some of these mistakes and maybe use them to self-correct it.
So I didn't think about it. So the question is kind of, can we have like a theory of model cognitive biases like we have for human cognitive biases? Yes. So I didn't think about it. Like, so I don't know. It's a good question. I'm generally just like, I kind of am a believer, just like we, in the first slide that I had, like with deep learning, I am kind of a believer that also for safety and alignment, we want to not have something complicated where we need to enumerate biases, but we want to have find something simple that scales and that we would be able to invest a lot of computing and get the model to be better. We haven't really not found that yet.
On that direction, I was thinking that maybe if we have some kind of like evaluating each other in an adversarial setting, the other model could learn a Swiss Army knife of its own, which could be scalable.
Yeah, that could be a case. Like the adversarial training is a thing, and people have been using it. We might even have some lectures on it. So yeah, with that, let me end and just again, if you're interested, if you're not registered to the course but would like to be, and you actually showed up and you're here, and hopefully you also maybe submitted homework 0, but maybe, I mean, you can talk to Roy and talk to him, and you can see what he can do. So thank you.